Hey everyone, I hope you all are safe and doing good. So, in the previous lecture, we have seen linear search algorithm. There is one more searching algorithm that is better than the linear search, and that is binary search algorithm. So, this thing we'll see in this video. What is binary search algorithm? Why we call it binary search, and how this is better than linear search. The obviously the core concept, like the working of binary search algorithm, and you can see the time complexity of this algorithm, and we will also see improved version of this, that is order agnostic binary search. Okay, so all these things we'll discuss in this lecture. First, what is binary search algorithm? See, in linear search, if there is an array given and you have to search an element from the given array, we compare that target element with all the element sequentially, linearly. We start from the first element and start searching, like we have something like this. So if you want to find out minus 1, if you have to find out minus 1, I mean, you have to search if minus 1 exists in this array or not. Then in linear search, we start comparing. Is this minus 1? Is this minus 1? Minus 1, minus 1. Yes, this is. So we return the index, something like this. And obviously, in the worst case, the element is at the last, or maybe the element is not present. So you have to compare with all the numbers, whatever the array size is, and the complexity is, we know in bigger notation, order of n. Right now, binary search is better than this, but very first let me just tell you one thing. The prerequisite to perform this binary search algorithm is this array must be sorted in ascending order, either it's ascending or descending order, but by default we assume that array is in ascending order. Okay, to perform binary search. So if array is something like this, it's not sorted array, we cannot apply binary search. First you have to sort this array. So array is something like this to perform binary search. Something like this. So this array is, we know, sorted in ascending order. Yeah, you can apply on this array binary search. Okay. Now how binary search works? Basically, we'll not start searching from the first element. We know this is the start or the low, or this is high. There are two pointers or two like variables we have. This is like two pointer approach. So either you can have the start, or this is end, or this is I, or this is j, or this is low, or this is high. It's up to you. Right. Now, first calculate the mid of this array. How to calculate mid? The index is C. We have 0, 1, 2, 3, 4, 5. Index is this. So low plus high divided by 2, that would be mid. So 0 plus 5 divided by 2. In integer, we are taking int, not double, because index is definitely int. So mid would be 5 divided by 2, so that is 2. It's 2.5, but we take int, so it's 2. Now mid is here. This is mid. So you need like basically 3 variables, right? So we have divided basically in almost this array in the half, almost half. Now, if the key, you want to find out key is equal to 11. Suppose target element is 11, you want to search 11 is there or not, because this is searching algorithm, right? Now we know, just compare this key with the middle element. You know this mid now, mid is 2. So we know we have the middle index. So we can directly access whatever is element at the middle, at mid. So like this, ARR of, if the name of this array is this, so ARR of mid will give you 8. So you compare the target element with this mid element. If it is equal to the target element or the key element, simply return mid. That's it. If it is 11, so return mid, and mid is right now 2. So yeah, we got our value. But if this is not equal to the mid element, and if this key element is greater than the mid element, now it's 11 is greater than 8. Can I now say that definitely this target element lie in this half? Yes, because we know array is sorted. If this is 8 and our target element is 11, that is more than 8. So we can definitely say that we cannot find 11 in this half. That would be definitely in right half. So we have reduced our search space by half directly. Even I mean, after only one comparison, because we have compared with this. So after one comparison, we have directly divided our search space into half. So you have to search in this half only right now. So now, if you have to search in this half, now this is our search space right now. Okay. Now we know, obviously, to search from here to here, we know the same approach you have to follow. Now again, find out mid of this and again the same approach. So now this high, this pointer is here only, but now this low or the start of this array is here, because you have to search from this to this. We have eliminated this part. So now you have to modify your low. So it's very simple. We can simply do low is equal to what? This mid plus 1. Mid plus 1. Now right now here we have low and here we have our high. Simple. I mean, not height, it's high. So just apply the same approach again, find out the mid, right? Again, compare with the mid. The target is 11 or not. I mean, the target is the same element or not. Now, again, compare. You have to search either in the right half or the left half because array is sorted, right? So this is basically binary search. Now, why this is known as binary search? I guess from this procedure you easily can find out, because binary means 2, we know, right? And repeatedly we are dividing this array into 2 halves. So that's why it is known as binary search. That's the reason. Okay. Now, see, binary search basically it finds a target value and it does this within a sorted array. The condition is the array should be sorted. It repeatedly divides the search space in half. Okay, so it is a searching algorithm. Now, why it's binary? Because as the name suggests, it divides the array in 2 halves. So that's why it's binary. Binary means 2. Until the same process we repeat until we find the element or search space is exhausted. Now, what does that mean? I'll show you practically. Don't worry. Okay. So if you want to find out, I mean, you have to write down the algorithm, then simply first step is what? You have to find out the middle element in the array. Second step is compare the middle element with the target element. Now within that you can write down if the target element is equal to the middle element, return mid. If the target element is greater than middle element, then search in the right half. If target element is less than middle element, search in the left half. Simple. And you have to repeat these steps until you find your until the target element you find in that array or the search space is exhausted. These are simple 4-5 steps. Okay, let me show you this thing. Let's take one example. I'll show you this thing, right? Then we will analyze the complexity as well. So we have this array, suppose. So here we have our low and here we have our high. You can take start or end or I or j, whatever variable name you want to take, you can take, right? The key, suppose the first case is you have to find out, suppose key is 5. You have to find out this 5 exists or not. Array is sorted, we can easily apply here binary search. We'll not go for linear search if array is sorted, because that would be, I'll show you the time complexity as well. And we know the time complexity basically is how many, basically the number of comparisons. Okay, I'll show you. Key is 5. Now in this case, can I say like low, high? Low is 0 and high is, we know, it's nothing but the index. It's 0 and it's 8. So first step is find out the mid. So 0 plus 8 divided by 2, that would be 4. So now mid is here. Our mid is here. Compare this. Is this equal to the key? Key you want to find out 5. 5 and 15. No, this is not equal. This 5 is less than the middle element. Means we will search, less than means it will definitely in this half only. That's it. You don't have to search in that half. Right? So obviously if low is still 0 but high, now you have to modify. Now high should be here because you have to search from here to here. That's it. Because we have eliminated that part. Now high becomes mid minus 1. That is 3. We know. Again find out mid, the same process. So we have like it's 0 plus 3 divided by 2. It's 1. Mid is 1 now. So mid right now is here. Now mid is here. And high is here right now. Compare. Is this 5? Yes, this is 5. We got it. It will return the mid, because right now mid is this, so it will return 1 and that's it. So we have only, in how many comparisons we got our answer? We have compared with this. This was the mid. One comparison and one, like 1 and 2, within 2 comparison, right? Now case 2 is, suppose we are having, you have to find out, suppose 50. Now key element is 50. See, again repeat the same step. Let's see. We are having our low is 0, high is same 8. So same step, mid, find out 0 plus 8 divided by 2, that is 4. So now mid is here. Is this equal to 50? No. Yeah, this key element is greater than 50, mid element, greater than 15, mid element, because it's 50. So definitely we know that this would lie here in the right side, the right half of the array. So you have to modify now low. So low becomes now mid plus 1. Now low is here. Now low is 4 plus 1, that is 5, and high would be as it is 8, this variable or this pointer. Now again find out mid. 5 plus 8 divided by 2, it becomes, it would be 6, right? Now our mid is here. This is now mid, right? So mid is here now. Now see, compare with this. 22, it's not equal to the key element, but key element is greater than mid. So we know that now we have to search from here to here, the right half. Yes. So again, this low is here. So now this is mid. So we know that now it lie within this. This is the search space now. So low would be here, high would be here. So now low becomes 6 plus 1, that is 7, and 8. So mid is 7 plus 8 divided by 2. So it becomes now what? 7, right? Because we are taking integer part. 7. Now mid is here, low is here, and mid is also here, because we have only like 2 elements. So low is same and mid is also same. Okay, fine. Now compare. Is 50 equal to the mid element? No. Yeah. Key element is greater than mid element. So now we have to search in the right half. But obviously the right half of this is only one element left. Right? So, but obviously we have to go to the right half. So we again modify our low. So low becomes 7 plus 1, that is 8. I mean mid plus 1, that is 8. And high is still 8. So now high is here, low is also here, pointing the same number, the same, you can say, obviously the element, because our search space has been reduced to 1. Now again find out 8 plus 8 divided by 2, mid, that is, it's 8. Mid is also at the same position, mid. Now compare, is this equal to mid? Yes. So return mid. Mid is what? 8. So it will return 8. And we know that at the 8th index there is 50. So how many comparisons? 1, 2, 3, 4. In just only 4 comparison, you got your answer, right? Here we have 50. How many elements? Total 9 elements. N is equal to 9. Even if n is 9, but this is at the last and within the 4. I mean, maximum you need 4 comparison and you got your answer. But if you go for linear search, you have to, how many comparisons would be there? 9 comparisons, because element is in the last. But now third case is, we want to find out, suppose 500. Element is not there. That can be a case. Okay, fine. Let's go for this. Now we have low and high, same process. Low is 0, it's 8. So mid would be 0 plus 8 divided by 2, that is 4. Now mid is here. Let's modify this a little bit. Now mid is again here. Is there target element equal to mid? No. It's greater than mid? Yes. So our element would be in this half only. We'll search here. So we have to modify low. Now low would be here. Mid plus 1. Low becomes 5. This is still 8. So 5 plus 8 divided by 2. It becomes again same process 6. Now mid is here. Right? Now compare. Is this the target element? No. Target element is greater than mid? Yes. So we would search in the right half only. So again modify the low. So low becomes again mid plus 1, that is 7. 6 plus 1, 7. 7 and 8. 7 plus 8 divided by 2, that is, again we got 7. Now mid is here. Now is this equal to this? No. But target element is greater than mid? Yes. So it will definitely lie in the right side of this mid. So in the right half only. But we still have only like search space is only one element. But still we have to go to right. So you have to modify your low. Low becomes mid plus 1, that is 7 plus 1, that is 8. This is also 8. 8 plus 8 divided by 2. Mid is also here. So right now, low is here, mid is also here, and high is also here because we have only one element. Now see, is this equal to this? No. Is this greater than mid? Yes. Means it will definitely to the right side. Yeah, right? Same process. One more step you have to repeat. If this is the right hand side, so we do what? We modify low. So low becomes mid plus 1, that is 9. 8 plus 1, 9. High is still 8. But now, see, this low is greater than high. Means we have moved here. High is here, low is here. Means it means that search space has been exhausted. There is no search space left with us. Right? We will search until this low is less than high or less than or equal to high. Once low becomes greater than high means there is no element to search in the array now. Okay. So element not found in this case. So there would be no like will not found mid and all. So here the loop will stop. So you have to put one condition also to terminate the loop. While this low is less than equal to high, till then we have to repeat these three, 4 steps. Now how many comparisons are there? 1, 2, 3, 4. Because we haven't compared here. So this is the worst case. Means element is not there. Within you go this answer you got within 4 comparison. And this n is 9. You got it? So there can be 2, 3 cases. This is how binary search works. So I hope you got this. Why this is known as binary search and how the core concept of binary search. The algorithm basically. First step, find out the middle element. Second step, compare the target element is equal to the mid element. Compare the target element with the mid element. If it is equal to mid element, return mid. If target element or the key element is greater than mid element, search in the right half. If target element is less than the middle element, search in the left half. Repeat the same process until you get your answer, or you can say the search space is exhausted. Till then, that's it. 4, 5 steps are there. Right? Okay. Now let's code it a little bit. Let me just do practically if it's working or not. Then we will discuss the time complexity for this and how this is better than linear search in terms of time complexity. Right? Okay, so in this project, data structure algorithm, we just want to create a new Java class and we are going for binary search. So at first, let's take an array. So we got this. This is an array. Let's have a method binary search. And what? We're passing the array here and the key as well. Obviously, you have to pass the key. So let's suppose you can take from the user also the number of, the elements in this array and the key using scanner object. You can just modify it. But I just want to take the key is equal to right now just 10 hard coded value. And we're passing the array as well as the to this. And it will return something, obviously the int value. So let's take a variable result. We'll store this here. Okay. Now let's define this method. So return type is definitely int. We are passing here. One is array. So that is basically the reference. So array, and second is we are taking int x. Same name you can take. It's ARR and here also ARR. Okay. Now you have to take first what the low. One is low and one is high. So high we know it's whatever the length of the array. ARR dot length minus 1. Yes, the index, if length is 9, then index would be, at the last index would be 8. So that's for sure, we know. Now, you have to do what? Main steps are, first you find out the mid. So int mid is equal to, we have this low plus high. Now we check. If we know the element is x is equal to whatever the element at mid. So in this case, we simply return, we know, mid. But if this is not the case, else if this x is suppose greater than ARR of mid, greater than this element, in that case, we know what happens. If it's greater than, you have to search, the target would lie in the right half. So you have to change this low. Now low becomes mid plus 1. Mid plus 1. This thing we know, right? Else, if this is not the case, then we know that if it's not equal to mid and this condition is also not true, so definitely that element would be in the left half. So don't need to write else if. You simply do high is equal to, what we do, high is equal to, we change high now, mid minus 1. This can be a case. Yes. So we are done with this. Now, this is what these steps would be. There is a condition to terminate these steps while this low is less than equal to high. Once it becomes greater than high, obviously you have to stop. Means the element not found, you have to print. In that case, return minus 1. So you have to put all these things we know within a condition while this low is less than equal to high. Till then you have to repeat these steps. Simple, right? Otherwise, if this condition is not true, if low becomes greater than high, then we know that at last the element not found and you have to return minus 1. Simple. That's it. It's very simple. Okay. Now you have to call this. Okay, we have called this function. It will return something. So based on that, you have to check if this result is not equal to minus 1, means we got the element, and you have to print the index where you got the element. Element found at whatever the index, it will return. Okay. If this is not the case, in else, you have to simply print element not found. That's it. Right? So let's try to run this. We want to find out 10. So it should print 0, 1, 2, 3. So element found at 3. See, we got it. Now if you want to change, let's suppose this key is 100. So 100 is not there. So it will return element not found. It will run and see element not found. Now if this key is, let's change it, and it's 2. So it should return element found at 0, because 2 is at 0th index. Yeah, we got it. So it's running. I mean, it's working. Okay, if you want to check, if you want to debug this, you just have to do one thing. You just add some breakpoint here, and now debug this how it's running. If it's 2 and you want to debug this, so let's debug this now. Debugging is very important. So it will definitely, it's like dry run. You are dry running this on this machine only, on laptop only. Dry run means basically, I mean you can do one thing. You can just have, just note down this thing on a piece of paper, and then you can just dry run that. You have to be debugger in that case, but here you have this debugger. So in this case, like, control is here right now. So we have array is this, x is equal to 2, because you want to search 2, we have passed this 2, e is 2. Array length is 9. So array length is 9. Step over. Now low is 0, and high is right now 8. So high is 8. See, let's step over. Now we have this thing, mid is equal to this. Okay, fine. Now let's run this. Now mid becomes 4. See, mid is 4, right? Let's run this again. This condition is not true. So control is in the else if. X greater than array of mid? I guess yes, because you want to search for 2. No, it's not true. Because key is 2. I mean, x is 2. Okay, and array of mid is, it's 4. So 0, 1, 2, 3, 4 is 15. This condition is not true. So we'll go in the else part. So high becomes now mid minus 1. See, high is 8, mid is 4 right now. But now high becomes 3. See the change. High is now 3, low is 0. So from 0 to 3, we want to check now. Again, check the condition. While this, yes, this condition true. While condition, enter here. Find out the mid. Now mid is 1. Right? Run this. This condition is not true, because this was not, 1 is 5, and you have to array of mid. Array of 1 is 5, and if you want to search for 2. So this condition was not true. Else if. X is greater than array of mid? No, this condition is also not true. So again into this else part, and high becomes again mid minus 1. So now high becomes 0, low is also 0. Again run this. This condition is still true, 0 less than equal to 0, yes. Now mid is again 0, mid is also 0 at 0th location. I mean this. Now it's true. Now x is equal to array of mid, because array of mid is also pointing to here. Now this is true, so it will return mid. Run this and say return mid means 0. It will return 0. So now result is 0. Result is not minus 1, it's true, so element found at 0. So it will print on the console now element found at 0 and then exit. That's it. This is how you can debug this. So this is basic like binary search. But one thing is, if let me just tell you the overflow condition here. Now one thing, we are writing what this, I mean start plus this. Let me just tell you here mid. How you are going to find out mid? We are writing simply this low plus high divided by 2. But this can be overflow condition sometimes. You have to modify. It's not correct, right? What we can do is, suppose this low and high. I mean high is sometimes, suppose it's a very huge number. Let's suppose integer dot max value. Whatever the max value. The max value is. So this is, we know that the maximum, the range of the integer max value 0 to here. Not 0 to here, from minus to 1, something like this, to this. 2147483 I guess, to this. We know this is the maximum value in plus. Suppose high is this, and at one place at one time this kind of situation exists. Low also becomes this, though both the low and high are the max value, because in the previous case we have seen now low is also there, high is also there at the maximum at 8. So there can be a case in this case also. Low is also this, high is also this. If you are going to plus this with this, then definitely it is out of the int range. So this is overflow condition. So that would be obviously in, it will not give you some kind of thing. There is that wrap up kind of thing. I have told you this thing. So by default it would be like negative value, and it would store in 2's complement. And if you go to plus this plus this again, then it would store ultimately as minus 2. Minus 2 divided by minus 2, it will give you minus 1. Mid is equal to minus 1, and we know that minus 1 doesn't exist. It's not a valid index. So this is overflow condition. If both low and high are huge number, if you are going to add both these numbers, then definitely it would be out of the int range. That is overflow condition. Now how to handle this? Obviously we have to find out mid. For mid, you have to do this thing. You can write down, the solution is, you can write down this thing. One way is, you can just take this mid and these as a long. That would be in range. But better is, why to take long? And we know that we don't need that much kind of thing, that long data type. So we can do one thing, we can just write down this thing in a different way. So we can write down this mid is equal to something like this. Mid is equal to low plus high minus low divided by 2. This is also as it is, like same as this. It will give you the same result, because we know if you going to compute this, then LCM is 2, and 2 into low plus high minus low, and ultimately it becomes low plus high divided by 2. This is the thing. But in this case, it will not give you like that overflow condition. If this both are same, then low is this plus high minus low. We are not going to add, we are going to minus. Then it becomes 0, then low by divided by 2, and you will be within the range itself if both are huge number. So rather than writing this, better way is, while you are going for binary search algorithm, better to write this. Okay. And in interview also, don't directly write down this condition. They know that, okay, you have the idea about those overflow conditions. That's why first I have just written this thing, and now why the cases I'm telling you, that overflow cases, and you have to switch to this condition. So now you can modify your binary search program. Rather than this, you have to write down this thing. You got it? Overflow condition, you got it? Now let's discuss about time complexity. Okay. In linear search, we know it's order of n. In binary search, it's log n, but why log n? See, we know that suppose we are having n elements at first, right? So at first there is no comparison. At first, right? N elements are there. Now in the second step, you find out mid. Mid is here. So we have divided this in this half, or I mean two half. So we know that our element, if it's mid, so directly it will give you the result. So that is the best case, means order of 1. Only one comparison you need. We know that time complexity, while going for time complexity, we basically focus on the number of comparisons you have done, right? So you have to find out maximum number of comparison for worst case complexity. Got it? Okay. Now we have divided our space in two half. Either you will search in this or this, but definitely in two half. Suppose we are going for this half. Mainly right now it's n, so here we have n by 2. This is also n by 2. So this is n, this is n by 2. Search space is now reduced to n by 2. In the next step, it's again divided. We know. So now element would be either in this half or this half. So we have divided into n by 2 divided by 2. That is n by 4, n by 4. So it becomes n by 4. And in the next step, it becomes n by 8. Because again, we divide this something like this. If you are having this, then again we divide this into half. Suppose element is there, so again we divide this into half. So this becomes like n by 8, n by 8. N by 4 divided by 2, so it's like n by 8 only. Right? Like this we are going. Right? Now, see, ultimately at the end we will reach to, like, the search space will becomes only 1. In the worst case, if element doesn't exist, we know in the previous case I have shown you, at last you get that there is only one element and you have to search there. The search space is only one element you have, so only one. So it's 1. Like this we are going. So like this we are going from here to here, then here, then here, and here. So here there were no comparison at first. At first we haven't compared anything. We compared after dividing it. We are comparing after finding mid. We are comparing with this. We know at first we are having n. There is no comparison, so 0 comparison. Here we are having 1 comparison. Here till now we have done 1 comparison this and 1 with this mid. So basically 2 comparison. Here 1 was this, 1 is this, and 1 is this. So 3 comparison like this. Then 4 comparison like this. Right? So can I write something like this? It's n, so n divided by 2 raised to power 0, n divided by 2 raised to power 1, n divided by 2 raised to power 2, n divided by 2 raised to power 3. Here 0 comparison, so n divided by 2 raised to power 0. 1 comparison, so n divided by 2 raised to power 1. 2 comparison, n divided by 2 raised to power 2, something like this. Right? Then 3 comparisons, then, or you can say in level 3, n divided by 2 raised to power 3. So this is equal to 2, whatever the power you have of 2, it's equal to the number of comparisons. At last, we got 1 space. So suppose here we have done, like, it's kth level or k comparison. Up to this, we have done k comparisons. So can I write this one as it's n divided by 2 raised to power k? With the approach, whatever you have done, with the pattern, right? Because we have 0 comparison, so we can write n divided by 2 raised to power 0. So ultimately, after some comparison, suppose kth comparison, we got search space 1. So can I write with the same pattern? 1 is equal to n divided by 2 raised to power k. Simple. It's a little bit mathematics. So we can write 1 is equal to, it's not that much tough. If you are not getting this, n divided by 2 raised to power k, you just watch this video again a little bit. It's not tough. Okay. If you go through this pattern, then you will easily get why I'm writing 1 is equal to n divided by 2k. Now, how to solve this? It becomes 2k is equal to n. While solving this, so ultimately we have to find out the value of k to find out the maximum number of comparison, because we know that after kth comparison we got this thing. So you have to find out k, means in the worst case how many comparisons you required, and that would be your definitely the time complexity, by ignoring all the other constant and all. Ultimately, generally, we know that we consider that the number of comparisons only. Okay, the number of operations or the comparisons, right? Now we have to find out value of k. So how to find out? In this case, if you are a little bit aware about maths, you to find out this type of value, we take log on both side. So take log on both side. Once you write down this, so k will be here and it becomes log 2 is equal to log n. And if you find out k, then k becomes log n divided by log 2. And you can just write down k is equal to log of n basis 2 divided by 2. Then we can write down this something like this. Now, these many comparisons or maximum, and sometimes you get number of comparisons are this plus 1. But we ignore that 1 and all while writing bigger notation. So time complexity would be log of 2n. Because in this case, in the previous case I have shown you, we are having almost 9 element, and if you have 9 or 10 elements, suppose 10 elements, then maximum you need 4 comparison, 4 or 5, that's it. Okay, to in the worst case. And if you get log value of 10, it's approximately 4. Log value of 10 base 2. So if you get like this thing, log of 10 base 2, it would be 3.9 something. So it's like 4 approximately. And at most, in worst case, if 10 elements are there and the element is not present there, you will need 4 or 5, maximum 5. So the number of comparison maximum is 4 plus 1. I mean, log of 10 plus 1, that's it. You get the result, you get the answer. And we ignore this one. So in bigger notation, we write this thing. You got it? Now, if there are 500 elements, then maximum, because we are, if you have 500 element, if n is equal to 500, so we know that in linear search, in worst case 500 comparison you need, it's order of n, but in this we are dividing this by half. So this is one comparison, we have compared this one comparison. Now plus either this or this, you have to search. So you have divided the space by 2, 250 and 250. So suppose element is at this side, so again divide this by 2. So one comparison is this, one comparison. Again you have removed the this, it would be 125 or 125 search space. Again divide this. In worst case, I'm telling you, right? Again divide this. Now one more comparison you have done with this mid. Now again you have divided this. So it's almost like maybe 62 and 62 or 63, right? So like this you again divide. Then at most, in worst case, you require 9 or maximum 10 comparison to get the result. In worst case, if element is not there in this list. So you need in 10 comparisons, suppose let's say 10 comparisons, you get your answer. In linear case, you have to do 500 comparison. If suppose data set is having 1 million data. So linear search, you require 1 million comparison. And here, 1 million, in this case, log of 1 million, you can just easily find out on the Google. It would be really less. Okay. So now I hope you got this, why this one is better. And log of, if you get log of 500, it will give you almost approximately 9, 8.9 to something like this. So approx 9. So the number of comparisons are 9 plus 1, that is 10. So log of n plus 1, number of comparisons maximum. Okay, that's why. Now if you are aware about this log values and all, then you can easily find out that how your graph is going on. Like this graph, the time complexity graph, number of comparison, number of operations, or the size or input size. So how this is going, it's basically something like this. Sorry, it's logarithmic. So it's something like this. Linear is something like this, something like, I mean linear, a line, something like this. Let me just draw this again. Linear is, we know, something like this, but log is something like this, something like this. So there's a huge difference when the data would be increasing. See, in the number of operations, there is a huge difference. So that's why obviously log n is better, right? Now you got now why time complexity is order of log n and why it's better than the linear one. Linear, but the prerequisite is here the data must be sorted. But now we have seen The data was in ascending order. See, data is ascending order. We know data is ascending order, so we have write down our code. But what if data is in descending order? Now you know that data is in descending order. The array is in descending order. Now how to apply binary search? Very simple. Suppose this is the data. This is in descending order. Yes. So same approach you have to apply here also. And in advance, you know the data is in ascending order. So we have only 9 elements and this is a low, same, this is a high. Again, you have to find out mid. So mid is definitely we know this would be mid. But now if key is suppose I want to search for 22, you have to change this condition a little bit. You can just pause the video and try this out. This is the array descending in descending order. I want to find out 22. You have to apply, binary search definitely have to get how you know the logic. You have to change a little bit. Now, if it's 22, then see, check with mid. This is 5, this is 22. It's not equal. Now, we know that our key or the target element is greater than our mid element. So, in the previous case, if it's greater than, then you have to search in the right half, we know. But it's in descending order. We know that mid is 5. So, definitely on the right half, elements would be either 5 equal to 5 or less than 5. 25 would not lie in this part, right half. So in this case, now you have to search in the left half. Now high becomes this. So now high you have to change. If this is greater than, then high becomes mid minus 1. If the key is suppose 2, so this is 5, it's not equal, but our data is less than mid. So we already know in advance that array is in descending order. So we know that the data would lie in the right half only. So we can change. In that case, we change low is equal to mid plus 1. A little bit you have to change. Right? Now let me show you practically this thing. So let's take a new array and we are going for now the array is descending order. Suppose we have an array ARR of 1. This is in descending order and this array is ascending order. Now I want to here pass this array of 1, array 1, ARR 1, this array which is in descending order. Now you have to change this a little bit. Now what to do? Low and high, while less than low, this condition would be as it is, mid would be as it is. If this is mid, return mid, but this condition would check. If x is greater than now array of mid, then now you have to change here high becomes mid minus 1 because array is in descending order. Else you have to change, comment out this. Else low becomes mid plus 1. That's it. And that's it. We are good to go now. If the key is 2, so 2. Let's run this and see. What output you will get here? 0, 1, 2, 3, 4, 5, 6, 7, 8. So element found at 8. You got it. If this key is suppose 22. So this is at 0, 1, 2. So element is at 2. Second index. We got it. So I guess that's not that much tough. Right? But one thing. Now, okay. I guess you got it. Time complexity would be as it is. But one more case is there. Let me show you. So we got the time complexity as well in best, average and worst case. We don't consider generally average case. We go for worst case or best case. Okay, but in average and both worst case it's order of log n. In best case it's order of 1 itself. Now overflow cases also I have told you. If you do start plus this, then it would be overflow out of int range. So better to write down this thing. Now next thing. If in advance you don't know array is ascending or descending, in that case how you will go for binary search? If you assume that like obviously array is in, we assume when you go for binary search, we just take simple example array is in ascending order and we apply that thing. But if interviewer ask, you don't know array is in ascending order or descending order, that is for sure. One thing is it's either in ascending or descending order and you can apply binary search easily. We know how to apply binary search when array is in ascending and descending order, both the things we have seen. both the logics. Now you know, but at first you have to find out now how to check first. So the solution is you have to apply now order agnostic binary search. In this case, first we will check array is in ascending order or descending order, and then we apply according to whatever the situation. If it's ascending order, that logic. If it's descending order, different logic. The conditions. I mean, logic is same, only the condition is a little bit different. That's it. Okay, but first, how to find out, that is a crucial part. Now, if suppose array is something like this, how to find out? Maybe you say that. Just pause the video and think about it a little bit. How you will get to know that array is in ascending or descending order? Maybe you say, okay, compare this with this. First element with second element. In ascending order, if this element is greater than the first element, we know that this is ascending order. Because if it's greater, we know that all the elements would be greater than this. And then apply the logic. Okay, fine. Let's suppose it's 10. Both the elements are same. Then we can't simply compare this and because these are equal. So it can be ascending or descending order. It can be a case. If it is also 10 in that case. So what is the best scenario? What are the best two numbers you can compare to find out that it is ascending or descending order? Think about this. So the best element to compare are this and this. First and the last element. If all the elements, if this is 10, the 10, 10, 10 and this is 10. So we know that obviously in array we are having only one element, that is 10 itself at all the positions. But the best two elements to compare are this and this. If this last element is greater than the first element, then we know that it is in ascending order. If the last element is less than this, then it is in descending order. Equal to lie in either descending or descending case. Okay. So how to check? We can check like we can have a variable. Now while applying for the condition, now you have to check if it is in ascending order, apply these if else. Otherwise, apply the descending case if else. So first you have to check. So we can take something like a boolean variable. Boolean is ascending, right? At first, maybe you can set it false. And now you check. If ARR of low is this less than ARR of high, this element, then we can set this is ascending is equal to true. Simple. And while applying those conditions, you check if is ascending is true, apply that case. Now, if it's less than, then it's ascending. If it's equal to or less, equal to or greater than this element, then it will lie on the second case, that is descending order. You got it? Now, pause the video and try to write down a program for this. I guess you got it. First, you have to determine the order, then you have to apply the logic accordingly based on the array order, and same continue the normal binary search process. We know the binary search process, same thing you have to apply. Okay, let's now practically see this thing. So what we can do is, let's just create a new Java class here. It's order agnostic binary search we are discussing. So same array, let's change the name of the method. It's order agnostic binary search. We are passing here ARR1, that is descending order, but obviously we will check first. So let's define this method here. So we know the same thing. First we will have low and one variable is high. That would be, array of length -1. Then we have to find out if it's ascending or descending. So for that we can take a boolean variable. Boolean is ascending. Let's not initialize it. And what we can do is here, if it is true, then we can assign it true. If its low is less than ARR of high, this is true. Simple. So now it becomes true. Otherwise, by default, we know that it would be false. So otherwise, else, or you can say else it's false. So we can simply write here is equal to first false. It will change it. Otherwise, it would be false as it is. False. Okay. Now, let's, we know the condition now. That would be low less than high. Till then, we are going to repeat the steps of binary search. Got it? Now, what you need to do first, obviously, we have to find out mid. So, mid would be, it's now low plus, sorry, we know high minus low divided by 2. This is the mid. Don't just do low plus and bracket this bracket and divide by 2. No, it would be, it would be wrong. It's simply high divided by 2 every time. Divide by 2 is only high minus low divided by 2. Low is separate. So we have calculated mid as well now. Now check. First check if, rather than checking if it's ascending or descending, we know that first one case is common in all the cases if array is ascending or descending. If its array of mid is equal to, or whatever your element x is equal to array of mid in both the cases, then definitely it will return, this is the common case, is equal to array of mid double equal to, sorry, then it will definitely return mid in both the cases. So this is the common case, right? Okay, fine. Now check it's ascending or descending order, because whatever condition now you apply, it depends on the type of array. So now if this is ascending, if it's true, in that case we check, means it is in ascending order, ascending, right? If it's true, then we check if your x is, we know, greater than the mid, then we know that the element is in the right half because array is ascending. So we have to change the low. Now low becomes mid plus 1. Simple. Right? Else, we know you have to change the high. So else high becomes mid minus 1. Very simple. Right? So this is else part and this is if. If it's true. Now after that, else. We know in else, we know that if it's not ascending, it would be in descending order. So apply those things. If, let's just copy paste the same thing because you have to change a little bit here. So if this is greater than array of mid, now here you have to write down this one because array is in descending order. And here you have to change low is equal to this. Low is equal to mid plus 1. I hope you are getting this. It's not tough. Right? So this is descending case. Otherwise, if the element is not there, then after completing this while loop is ended here. See, this is closing of this while loop. After while loop, we have to return minus 1. So simply write here return minus 1. Very simple. That's it. So if you didn't get it, just pause the video, write down this code on a piece of paper, dry run this. Okay, you will get it. Now I'm passing here now at this point of time ARR of 1, ARR of 1. And I just want to check 22. Where is 22? He is 22. Let's run this. And it will give you 0, 1, 2. So it is second index 0, 1, 2. Yes. Now 22 is here itself in array ARR of 1. It is in ascending order. Now let's pass the array ARR, this array. And again, same search for 22. So let's run this. It will give you 0, 1, 2, 3, 4, 5, 6. See, element found at 6. Means the logic is correct. In this case, it's at 1, 2, 3. It's, in this case, it is at 6 location. So both the arrays you can pass and you can check. You can find out. So if you're not getting this, either you can debug this code. In this case, if you want to debug this, suppose right now we are passing this array, right? So you can just debug this. You can just, we know how to debug. Add a debugging point here, or the breakpoint here, and now debug this. So array is this. Array is this. The variables are x is 22 and array length is 9. We know. Step over. Now we know that. high is here, low is 0, high is 8, array length is 9, array of low is 2, and array of high is 50. Boolean is ascending is false right now. Check the condition. Condition is true or false. Let's run this. Now its condition is true. So it becomes true. See, is ascending is right now false, but as soon as I step over, it becomes true. See, it's true. Now this condition is also true. Calculated mid is equal to 4, we know. Now run this. Now is condition is ascending was true, so control will go in this if else statement. See, it is true, so we are going to enter in this loop, in this if condition, right? And then we definitely get it. So you can debug this right now, and key is 22, ARR of 1 is this. It will give, if you run this, so it will give you a result element found at 6, right? After passing ARR1, you can again debug this, and you can check it will not go to into this if part, it will go to into this else part, because at that time is ascending is false. Now if you don't want to write down this in the 2-3 lines, we can simply write, rather than this, what we can do is ascending is equal to, write down directly, you can write down this condition. So let's just write down, rather than false here, this condition as, comment out this thing, simple. So it will return true or false. Based on that, boolean is element would be assigned the value, simple. Right now if you run this, same, it will give element, we are searching for 22, so it is in 16, sorry, 6th position. So you can write down this thing in same one line itself, or if you are not comfortable in this, you can just go for those 2-3 lines, right? So this is order agnostic binary search. So we got it, this thing. Now why binary search is better? We know the speed, it significantly reduces the search time, because the number of comparisons are less. Time complexity is order of log n, and fewer comparisons, so that's why it is more efficient than the previous case for large data set. If you have small data set, 5, 10, 50 elements or 100 elements, you can go for linear search. But for huge data set, 10, suppose 10,000 element, 1 million element, then go for binary search. In that case, you will see the difference in the, obviously, the time taken by executing that program. Advantages, we know it's efficient because of logarithmic time complexity. Then it is ideal for large data set, and it's not that much tough. It's easy to understand. It's not that much tough. Drawbacks, one is, prerequisite is you have sorted data. It will not work on unsorted data. If there is unsorted data, you have to sort it first, then you can apply binary search. Okay. Insertion and deletion are a little bit not, it's efficient for frequent data modification, because yeah, see, I'll show you how to insert and delete if the array is sorted. When you go for those, you have to find out there are duplicates element in the array, and you have to find out first occurrence and the last occurrence of that element. In that case, if array is sorted, we go for binary search. So for that, we apply another technique like lower bound. We find out lower bound, we find out upper bound in that case. So show this. I'll show you this thing in the next video. But it's not definitely good for frequent insertion and deletion. Okay, this is one Java code for binary search. We have seen this thing. Some real world example while searching in the databases or the large data structure like B tree and B plus trees. There, binary search is being used to search. Okay, in dictionaries, while spell checking, in that case also binary search is used. Competitive programming, coding interviews, this is, then the question you have seen, I told you, find the first occurrence or find the number of duplicates, find the last occurrence of this letter of this element. So there are so many lead code questions, or code chef, or there are so many coding platforms. There you get many questions uses binary search. You can solve those questions by using binary search efficiently. There can be many approaches, but efficient approaches using binary search. In internet, like a router used, if they want to look up the IP addresses from the array, and the IP addresses are in sorted order, so there binary search is being used. In e-commerce and online libraries, they are searching for books on Amazon or any library databases, then this is being used. In Git also, if you want to find out the commit that introduced a bug in the Git, so Git bisect, then there binary search, this algorithm is being used to find out which Git has introduced this bug, which, sorry, commit has introduced that bug. So there are so many applications of binary search algorithm, real world applications. Okay. But ensure that the data is sorted while applying this thing. And you have to handle the duplicates as well. If the array is having some duplicates, if suppose this is the case, I am having this array. There are so many duplicates in my array. Suppose I'm 2, 2, 2, 2, 2, and 3, 4. Now I want to find out for 2. I want to search element 2 exists or not. So linear search will give whenever it finds the first index, but binary search will give you divide by half. So we have it's 7 by 2, I guess. 1, 2, 3, 4, 5, 6, 7, 8. So 7 by 2, 3. Mid is this. Binary search will give you index 3, linear search will give you index 2. So like this. Okay. But yeah, if the duplicates data is there, then we have to follow another approach. So you have to handle this thing carefully. In this case, you can go for lower bound. If this is the case, then go for lower bound as well. Where at first occurrence, where is the first occurrence of this 2? You definitely, if you go for lower bound, then you will get at 0th index the first occurrence of 2 is there. Or you can go for the last occurrence if you want to find out, then go for the upper bound. So here you will get the last occurrence. Okay. I'll show you in the next lecture how to implement this lower bound and upper bound in binary search. Don't worry. Okay. So this thing we'll see in the next lecture. But basics are, I guess, clear to you. Binary search, why it is better than linear search, and what is order agnostic binary search. But if we have duplicate kind of data, then how to apply binary search and these things, that thing we'll see in the next lecture. Right. So I hope now everything is clear to you, whatever we have discussed in this lecture. Now I'll see you in the next lecture. Till then, bye bye. Take care.